So we're going to look at some what are called inverse matrices today. So take you back for a second to the identity property of multiplication. So if you're multiplying 1 times any other value, it doesn't change the result that you had to start with. There's a special matrix so that if you multiply this matrix times any other matrix, you still get your original matrix back, and that matrix is called the identity matrix. So the 2 by 2 identity matrix is the matrix with 1s on the diagonal from upper left to lower right corner, and then 0s everywhere else. And there are other sizes of square identity matrices. You could have 3 by 3 ones, 4 by 4 ones, as long as you have 1s down the diagonal and then 0s everywhere else. So we're going to do a little verifying, and I'm going to show you that if you multiply the identity matrix times any other matrix, you still end up with your original matrix. Don't take my word for it, let's see it. So if you do this multiplication, I like to label, so I've got a 2 by 2 matrix times another 2 by 2 matrix, so my result is going to be a new 2 by 2 matrix. If you think about your elements being multiplied, I need to get my element in the upper left corner, row 1 times column 1. So let's do 2 times 1 is 2. Then we'll move to the next element. -4 times 0 is 0. Moving over for column 2, we've got 2 times 0 is 0, plus -4 times 1 is -4. And then on down to row 2, 6 times 1 is 6. And then 7 times 0 is 0. And our last element, 6 times 0 is 0. 7 times 1 is 1. So if you actually do that, you're going to see that we get our original matrix A back. So multiplying by our identity matrix did not change the matrix that I got as a result. Let's think about the inverse property of multiplication for a second. It says that there exists a value that I can multiply any number by to get back to my identity element for multiplication, which is 1. So I can multiply 5 by its reciprocal 1/5 to get back to 1. Matrices can also have inverses that you multiply by them to get back to the identity matrix. So if you have a square matrix, it might have another matrix so that when you multiply them back together, you get the identity matrix. Notation-wise, that matrix is what looks like to the -1st power, but that means your inverse. So how do you find the inverse of a matrix? Tomorrow we're going to use inverse matrices to solve some systems of equations, but today I'm going to show you how to find the inverse first. So first thing we do is go ahead and write your original matrix, and then we're kind of going to augment it with the identity matrix of the same size. So we had a 2 by 2 matrix. I tack the 2 by 2 identity matrix on the side of it. And then I'm going to run through the process that I use for Gauss-Jordan elimination. So I need a 1 in the upper left-hand corner. So I'm going to divide that entire first row by 2, including the elements in my identity matrix on the right-hand side. And then I'm going to rewrite my new matrix. Next, I need to work in that column to get the rest of my values zeros. So if I need a 0 where my 3 is, I'm going to multiply my top row by -3 so that I have that to add with my bottom row to get 0. And don't forget to do it to everything on the right-hand side as well. So if I add those, I end up with a new second row of 0, 5 halves, -3 halves, and 1. And then I'm just going to keep going until I get my matrix on the left to have 1s along the main diagonal and 0s everywhere else, which I realize I forgot to mention in my other video is called row-reduced echelon form. So I need my 1. I'm going to multiply that row by 2/5, which is going to get me, let's see, I'll go ahead and go 0, 1, multiplying -3 halves times 2/5 gives me -3/5, and 1 times 2/5 is 2/5. Rewrite my first row. And then my last step is going to be to get a 0 in the upper right-hand corner there. So I'm going to multiply my bottom row times my positive 1/2, and then I'll be able to add them together to get 0 there. You'll have 1, 0, 1/5, 1/5. So once I have completed my elimination process, the matrix that I have on the right is my inverse of my original matrix. So don't just leave it there, go ahead and write it separately. My inverse matrix for my original is that matrix right there. Now we're going to check and make sure that we did this correctly, so you can see if you did it right, it's supposed to multiply to get you the identity matrix. So multiplying them together, 2 times 1/5 is 2/5. -1 times -3/5, positive 3/5. Upper right hand element, 2/5 plus -2/5. It's looking good so far. 3 times 1/5 is 3/5. -3/5. 3 times 1/5 is 3/5, and then 2/5. So you can see if you go ahead and add those together and simplify, you do get the identity matrix back, so our two matrices are inverses. There may be times where you just want to see if two matrices are inverses, so you don't need to find the inverse to do that. Just multiply them together and see if you get the identity matrix. If you do, they're inverses. If not, then they're not. Not every matrix has an inverse, so let me show you what it's going to look like if you're trying to find the inverse of a matrix and that doesn't actually exist. So if I'm working through my process here, and it's all looking good so far, I got my 1 in the upper left-hand corner. Now I need to get my zeros along the rest of that column, so I'm just going to rewrite that second row. Need to multiply my top row times 3 so that I can add those together and eliminate that to get a 0. I end up with 0, 0, 3/5, 1. Now if you try to continue on, you're going to run into a problem because your next step in your process to get a 1, but you have a 0 there, and there's no way to really make that into a 1 and still have equivalent values represented in my matrix. Much like when we had that row of zeros in our Gauss-Jordan elimination and then a constant on the right that was non-zero, it indicates that it's not possible and no inverse exists. If you want to save yourself a little bit of work, you can check to see if an inverse of a square matrix exists before you try to find it by finding the determinant of your matrix. So if you find your determinant, like we did for Cramer's rule, and you get 0, that means your matrix is what's called non-invertible, and it has no inverse.